All right, gang, welcome back. I'll put you out of your misery now. I have not graded your test yet. My general rule for grading exams is a turnaround period of about 1 week. So my goal is to have those graded for you by Thursday. I did receive a few emails kind of in this panicked tone saying, oh my God, my exam grade is like a 22%. I'm fucked, what do I do? Remember, I haven't graded the test yet. So that score is just counting your true, false, and multiple choice score. Right now, everybody has a 0 for all 6 free response problems. That would put even a perfect test into F territory. So please don't panic about your test grade as it's listed in Canvas right now. Right now, everybody has a 0 on all the free response questions. So even if you did perfectly, it's still going to show as less than 50% because the free response is worth, 60 points out of 100. I will be getting those graded as quickly as I can, and my usual rule is 1 week. I'm planning to do that for you guys as well. So by Thursday, you'll know your test grades. Okay. I think that's time to do this today. Oh, excuse me. So this is MAC1140, section 009. Pre-calc class, and today is the 28th. We begin today the second part of the class. The second leg of this class is kind of a detailed study of different function types. So we've talked about functions in general, right? In chapter 1 and chapter 2, the heart of our discussion is functions. In chapter 3, we are going to talk about polynomial and rational functions. And we're going to study them in great detail, kind of through the lens and using the notation and terminology that we have used thus far with general functions. This is going to be detailed. We're going to be learning lots of new specific skills. And you're going to be looking at these things, even if you've seen some of them before, like polynomials, I'm sure you've seen before. Even if you've seen them before, we will be looking at them from a new perspective, a slightly more enlightened perspective, and a slightly more willing to work perspective. That's about all I need to say about this. So let's go ahead and get to it today. We're going to go through section 3.1 on quadratic functions. And I'm sure everybody here has dealt with quadratic functions in the past. So we're going to move through this somewhat quickly. Whole section definitely going down today. We're also going to talk or begin talking a little bit about polynomial functions in general, which is section 3.2. So quadratics are special polynomials, but there are many polynomials that are not quadratics. I'll warn you at the start. Some of the terminology that your textbook uses, some of the language they use in the quadratic section is not normal. I don't know why they do this, but I'll tell you when we come to it. We're going to come to it right away. So let's go ahead and begin. A quadratic function is one which can be written as f of x equals ax squared plus bx plus c, where a is not 0. All right, so a, b, and c are constants, they're numbers. And I require a to be something other than 0 because if a is 0, then this term isn't really here. And we all know it's the x squared that makes this thing a quadratic, right? If it was just like bx plus c, that's a linear function. So we definitely don't want a to be 0 because then this thing really isn't a quadratic. Quadratic, the word comes from Latin and it has to do with this 2. Now, most people call this ax squared plus bx plus c the standard form. But your textbook calls something else the standard form. So the thing that your book calls the standard or vertex form is this. F of x equals a, and the a here is the same as the a here, times x minus h all squared plus k. So most books call this the vertex form because you can read the vertex of the parabola off from it. Our book calls it the standard form. So in your homework, when you see, put this quadratic into standard form, they want it in this form. This is what they mean by standard form. Okay, and again, the a here is the same as the a here. So if you had 5x squared plus blah, 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 then this in the vertex form is going to be a 5. The graphs of these things we all know. They are parabolic. So H, K, point H comma K, which we call the vertex. So you see, if I give you a quadratic in this form, you can tell me what the vertex is. And if A, that lead coefficient, is positive, the parabola opens up. And this picture is what we mean by opening up, right? The parabola kind of has this bowl shape, and the open part of the bowl is pointing up. So we say that this is opening up. On the other hand, assuming H and K are similar as they were before, but if A is negative, then the parabola will open down. And this picture is what I mean by opening down. The vertex in both of these is the same, the point H comma K, and that's the usual notation for labeling the vertex of the parabola. This point right here is called the vertex. This point right here is called the vertex. And these graphs all have some symmetry, right? They're always symmetric about this line, a vertical line going through that vertex. Some people call this thing the axis of symmetry. So I don't remember if it was in this class or in another class when we talked about even and odd functions. Somebody asked me, are all parabolas even functions? No, not necessarily. Only if their axis of symmetry is the y-axis. But they do all have an axis of symmetry. They are all symmetric about the vertical line through their vertex. So they all exhibit the kind of symmetry that you talk about with an even function, but that axis of symmetry isn't always the y-axis. It can move around. The reason that the vertex form or standard form is so nice is because you can think of this as a transformation of x squared. This is a transformation of the parent function x squared, right? We shift to the right by h units, we shift up by k units, and we're either going to stretch or compress vertically by a factor of a. So the vertex form makes it very easy to draw the graph. You just imagine starting with x squared and you move it left, right, up, down as the algebra tells you to do. In other words, once you have your quadratic in this form, it's very, very easy to sketch the graph. You get the vertex, or you think of it as a transformation of x squared, and you just plot the damn thing. It's not hard at all. But there's a question that we want to answer, and that is, how do we go from like ax squared plus bx plus c, whatever you want to call that thing, to the vertex or standard form, a times x minus h all squared plus k. And the answer here, I'll tell you, it's got a name. It's called completing the square. Revolves around coming up with this piece, the x minus h all squared. Like, how do you go from something that has like x squared, x, and constants to something like this? Well, at some point, you're going to need to do something factor e. You're going to have to factor something. And that full procedure is called completing the square. And I'm going to show you how to complete the square. I'm going to show you 3 examples because I think that's the best way to learn this procedure. And I'll tell you that the textbook does it one way and I do it a slightly different way. They're pretty much the same. Well, they are exactly the same thing. I haven't really chosen which one I like more. I think mine usually involves working a teensy bit more with fractions, but it's a little easier to understand. The textbooks involves like kind of ignoring one piece. I'll do my best to present this in a nice, clear, and obviously reasonable fashion. All right, so we're going to complete the square. This is a process that you use to rewrite something in this form into this form. And the reason it's called completing the square is because x minus h all squared is what's called a perfect square binomial, right? It's not like x plus 5 times x minus 3. It's like x minus 3 times x minus 3. It is a quantity times itself, and that is called a perfect square. So you're going to take this thing, which has is not a perfect square, and rewrite it as some constant times a perfect square plus some other constant. All right, let's do it. I'm just going to show you how to do it. It's not that bad, I promise. So I want to express the quadratic f of x equals 2x squared minus 12x plus 13 in standard vertex. I'd also like to find the vertex. Sketch the graph. And find the domain and range. All right, just for fun. So that's all stuff we should know how to do. Here's how you complete the square. I start with my 2x squared minus 12x plus 13. And I begin by force factoring out the lead coefficient, this 2. So I take that 2 and I open a big parentheses. 2x squared is going to become just x squared minus 12x is going to become minus 6x, and plus 13 is going to become plus 13 over 2. My next step is going to be to add and subtract something right here. I'm going to like add a number and I'm going to subtract that same number so I don't change the value of the thing. So I'm trying to answer a question here. And that's what number should come after the minus 6x so that I can factor a perfect square. So like x squared minus 6x plus 1, that's not a perfect square. X squared minus 6x plus 3, that's not a perfect square. What sort of number could I put right here, like instead of 13 over 2, so that x squared minus 6x plus that thing factors as a perfect square, like x minus 1 all squared? The answer is what I call the magic number. And it's always b over 2a all squared, where a, b, and c are these numbers. This is a. So here, b is negative 12 over 2a is 2 times 2 is 4. So that's negative 3 squared, or 9. 9 is the magic number that I would like to have right after this 6x. X squared minus 6x plus 9 factors as a perfect square. It's x minus 3 times x minus 3. In order to have that plus 9 here, I also need to subtract it. I can't just insert a 9 without fucking things up. But if you insert it and remove it, like this, you notice I haven't changed the value of the expression in the parentheses. It's still the same as it was in the previous line. I've added 0, right? The stuff under my finger adds up to 0. And the purple is the same as the purple from the line above. So I've added 9 and subtracted 9. Why 9? Because 9 is the magic number for this quadratic. Now, you can factor those first 3 terms as a perfect square. X squared minus 6x plus 9 is x minus 3 times x minus 3. That's just these pieces. I still have that minus 9 and plus 13 over 2. X minus 3 times x minus 3 is x minus 3 squared. There's your perfect square. And minus 9 plus 13 halves is whatever. I'll just leave it as it is. Minus 9 plus 13 halves. Now redistribute the 2. So you get 2 times x minus 3 squared minus 18 plus 13. Negative 9 times 2 is negative 18. 13 over 2 times 2 is 13. By the way, the only difference between the way I'm doing this and the way the book does this, they pull the 13 out to the side and basically just ignore it the whole time. So they would have the plus 13 out here instead of 13 halves in here. Literally the only difference. Finally, negative 18 plus 13 is minus 5. So this is 2 times x minus 3 squared minus 5. And that is completing the square. You see the thing we get out is in vertex form. This is in that Your book calls it standard form. Everybody else calls it vertex form. So we win. I want to pause here before we do the other stuff, find vertex, sketch graph, blah, 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 for questions just on this procedure. What would we like to ask about this? Everybody's 100% comfy? Okay. Yes, I'm teaching. All right, so now that we have this in this standard or AKA vertex form, we can read off H and K. All right, remember your standard form is A times X minus H squared plus K. So H here is +3 and K here is -5. Which means that your vertex is 3, -5. Remember that there's a negative kind of built into this form. So if I want to sketch the graph, it's 3, all this -5. My vertex is right here. And since A, the lead coefficient, is positive, the parabola is going to open up. So it's going to do something like this. There's a nice graph. Any questions about how I completed the square or how we got the graph? We think of this as a transformation of x squared, right? If you take x squared and shift it to the right 3 units, that would look like this. You shift that down 5 units, that's going to look like this. The 2 up here just stretches it vertically by a factor of 2. But the shape of the graph, the location of the vertex doesn't change with that. So you can get a really nice picture of the graph just by knowing the vertex and whether the parabola opens up or down. The other big thing we like to find are these x-intercepts. So the next big question is, how do we find the x-intercepts? Remember, x-intercepts, these are solutions to a particular equation. Solution to the equation f of x equals 0. We're looking where is y, which is f of x, equal to 0. Well, if y is 0, that means we're somewhere on the x-axis. So we're looking for those solutions to the equation f of x equals 0. These are also sometimes called roots or zeros. They're just other names for x-intercepts. Specifically, when we're talking about polynomials, you'll hear me call them roots all the time. So I'm going to start transitioning to that terminology now. Okay, the answer to this question comes in several flavors. If you're lucky, you can get them by factoring, right? If you know how to factor. If you're less lucky, you may have to use the quadratic formula. And we're going to prove the quadratic formula. Before I do that, let's draw on my axis of symmetry here. Let's find the domain and the range. What is the domain?
Minus infinity to plus infinity.
Yeah, good. All real numbers, right? Negative infinity to positive infinity. You could see that from the algebra here, right? There's no red flags. There's no variables under, downstairs in a fraction. And there's no variables inside even roots. There are no roots. There's nothing like that. So the domain is definitely all real numbers, or negative infinity to positive infinity. What about the range?
-5 to infinity.
Minus 5, positive infinity.
Yeah, very good. From -5, from the y value down here to infinity. And we always use a parentheses on the infinity symbol. What about the -5? Parentheses or bracket? Why?
Bracket because it's a point on the graph.
Very good. Yeah, that's exactly it. We're going to use a bracket because there is a point on the graph whose y value is exactly -5. Yeah, and I see something in the chat about the discriminant. We will talk about the discriminant a little later, but I want to prove the quadratic formula first. So we're going to talk about factoring. I'm going to show you how to factor. Something I want to point out. Look at these two distances here. Since that graph is symmetric about its vertex, right? Symmetric about this line. What is true of these two distances? This distance and this distance.
They're the same?
They're the same. Yeah, exactly. In other words, the x-intercepts are equidistant from the vertex, the x value of the vertex. So if you find your h, the x-coordinate of the vertex, then you know that your roots or zeros are kind of evenly distributed about that. I'm going to show you where this distance shows up in the quadratic formula, and I think you'll like it. But before we do that, I want to do a quick review of factoring. So finding how to find x intercepts, which are roots of a quadratic. Now remember what we're trying to do. We're trying to solve the equation f of x equals 0. So first, try to factor the thing. Worst case scenario here, you're going to use the AC method, which I'll remind you of. If that doesn't work, then you're going to use the quadratic formula. That's the vibe. Now, throughout all of anytime you're looking for roots or x-intercepts, you want to keep in mind that you're trying to solve the equation f of x equals 0. So if your function, if your quadratic is really simple, like x squared minus 1, then you can solve that without doing either of these things, right? You can solve that just by like adding 1 to both sides and taking square roots. But in general, these are your two main tools. Factoring, I'm going to give you some practice with these, and then the quadratic formula, I'm going to prove for you. Okay. Look at what I did here. So I'm going to give us two guys to work with. We're going to factor to find the x-intercepts, and we're going to sketch the graph. the first one, I will use x squared. Let's see. Let's do x squared plus 3x minus 10. Part B, let's do 3x squared. We'll call this guy g of x. 3x squared plus 5x minus 2. And both of these we're going to do by factor. We're not going to use the quadratic formula because I haven't shown it to you yet. We're going to start with this guy. If the lead coefficient is 1, if that number a here multiplying x squared is 1, then things are pretty easy. What we want to do is try to find, so this is still technically the AC method, we're going to try to find two numbers which multiply to -10. And in general, you're looking for two numbers that multiply to a times c, which here is 1 times -10, which is -10, and add up to the middle number, b, which in this case is +3. So can we think of two numbers which do that? Two numbers, I multiply them, I get -10, I add them, I get +3.
+5 and -2.
So here, 5 and -2 work. And that's all we need to factor. Now I can say, okay, f of x, which is x squared plus 3x minus 10, factors as x plus 5 times x minus 2. That's literally it, right? Nothing fancy. Once you find those numbers, you're done. So f of x is equal to 0 if and only if x plus 5 times x minus 2 is 0. And now each one of those parentheses things, each one of those factors represents a real number. This is some real number times some other real number. And the only way to have two things multiply and get 0 is if one of those things is 0. So either x plus 5 has to be 0, or x minus 2 has to be 0. That first one gives us x equals -5. And this other guy gives me x equals +2. From this, I can draw a reasonable little graph. I'm not terribly worried about scale here, just being rough about it. But I'll call this -5. I'll call this +2. And that means my vertex should be exactly halfway in between them. I don't know the y by vertex, but because this quadratic has a positive lead coefficient, a here is +1, I know it will open up, and I know those are the x-intercepts, and it has to look something like this. And if we wanted to find that vertex, we can, but we're not going to now. We don't need it to get a decent little graph, right? Just knowing that these are the x-intercepts and that the graph, the parabola opens up is enough for me to get a pretty good picture. If we wanted to find that vertex, we can complete the square. All right, and that would give me both h and k. But I don't need to know it for a little graph like this. Questions on part A? Okay, let's look at part B. So here I want to factor 3x squared plus 5x minus 2. And again, I need to try to find two numbers which multiply to a times c, which in this case is 3 times negative 2, which is negative 6, and add to b, which here is positive 5. So I'm looking for two numbers such that when I multiply them, I get negative 6, and when I add them, I get positive 5. Can we think of two such numbers? Two numbers, when I multiply them, I get negative 6. When I add them, I get positive 5.
Negative 6 and 1.
Negative 6 and 1, if I add those, I would get negative 5.
6 and negative 1, sorry.
Yeah, positive 6 and negative 1. All right, now here's the difference between these two. The first one starts off with just x squared, right? Not like 3x squared or 5x squared. The lead coefficient here is 1. This guy, the lead coefficient is not 1, it's 3. So I can't just jump immediately to the factored form once I find those two numbers. Since g of x equals 3x squared plus 5x minus 2 has a different from 1, we need to factor by grouping. So what that means is I'm going to take these two numbers, 6 and negative 1, and I'm going to use them to rewrite the middle term. They add up to 5. So I can write 5x as 6x minus 1x, and then factor that new thing by grouping. So here I'll have 3x squared plus 6x minus 1x minus 2. See what I did? I rewrote the middle term, 5x, as plus 6x minus 1x, and that's where these two guys came in. Now, as long as you chose these two guys correctly, you'll be able to factor this 4-term expression by grouping. What that means is you take the first two terms and the last two terms. You pull out as much as you can from each. So from 3x squared plus 6x, I can factor out a 3x. And that will leave me with x plus 2. And then from negative x minus 2, I can pull out a negative 1. And that will also leave me with x plus 2. And this is why these two numbers are chosen so carefully. On the one hand, because they add up to the middle term, I can split the middle term up using them. And on the other hand, because they multiply to a times c, when I factor out the greatest common factor from those two groups, what's left over will match. So you have an x plus 2 in both of these pieces. In other words, x plus 2 is a factor of this piece, and x plus 2 is a factor of this piece. So that's a common factor that I can pull out. And when I pull that out, I get 3x minus 1 times x plus 2. So I know that some people get through college algebra or other algebra classes without ever really mastering this AC method thing where the lead coefficient isn't 1. No mas, you got to get good at it. Now we can say, so g of x equals 0 if and only if the product of these two things equals 0. 3x minus 1 times x plus 2 equals 0. So from the first guy, you get x equals 1/3, and from the second guy, you get x equals -2. Those are your x-intercepts. Now, if I want to draw the graph, I can. Again, the lead coefficient is positive. So I'm just going to say the parabola opens upwards. And I'll plot these two x-intercepts and call that a day. So if I sketch this. Two. So 1/3 would be like right here. -2 is over here. And my vertex should be halfway in between them, somewhere around like this, opening up, and we look like this. This guy and this guy. And that would be an acceptable graph. You know, if you're just trying to figure out what this function looks like, you now have a pretty good idea what this function looks like. Any questions on either of these factoring methods? Or I guess this factoring method, the AC method? Okay. So what if you can't factor? All right. Trying to find the x-intercepts, the roots. First, you should try to factor, and worst case scenario, you have to use that AC method and factor by grouping. If you cannot factor, then you need to use the quadratic formula. We can't factor the quadratic. We get the roots using, it's a theorem. Quadratic formula. And I'm going to give you a fun way to remember this. First, let's write it down. This says that ax squared plus bx plus c will be equal to 0 if and only if x is -b plus or minus square root b squared minus 4ac all over 2a. All right, that's the formula. I'm going to prove this to you. So I think a lot of people, you see this, right? This is thrown at you in like middle school, and it's shoved down your throat forever and ever, amen, and all the algebra classes you take after that. But I think it's very rare that anybody shows you where the fuck it comes from. I'm going to prove it for you, and I'm also going to help you understand it geometrically, right, in terms of those distances. Before that, here's how you remember this forever and ever, amen. You know how like sometimes you're falling asleep, your brain does that thing where it reminds you of that really embarrassing thing you did back in 6th grade and it fucks up your night? You're going to induce one of those. So the best way to remember this formula is to go out into your life and find somebody you respect deeply, somebody you want to like you, somebody you want to impress, somebody you want to think you are cool. And you are going to embarrass yourself hugely to them. So, your crush or someone in your family you look up to, or always trying to earn the approval of, or something like that. You walk up to that person and you sing to the tune of Pop Goes the Weasel. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. And the shame from that moment, the deep, deep shame that you will feel will ensure that that moment will be one of those moments that pops up into your head as you're about to fall asleep, all comfy and happy, and just reminding you how embarrassing that was, because it really is. It sticks there. So I encourage you to do that. It will work, I promise. All right, where does this come from? We start with ax squared plus bx plus c equals 0 and complete the square. Then solve for x. So I'm going to write the 0 on the left-hand side, so I don't have to keep writing it. I'll just write a chain of equalities. 0 equals ax squared plus bx plus c. We want to complete the square, so I'm going to factor out the a, and that will leave me with x squared plus b over a times x plus c over a. We can divide both sides by a, and we get 0 is equal to x squared plus b over ax plus c over a. So I just start dividing out by a. Now, I add and subtract my magic number here. So this is going to be x squared plus b over a times x plus b over 2a squared minus b over 2a squared. And then I still have my plus c over a. Now, if you look at these first three terms and you ask, how does that factor? A is 1, right? This thing is 1. This thing is b over 2a all squared. And this thing is b over a times x. So I want to find two numbers that multiply to b over 2a all squared and add up to b over a. Well, that's b over a and b over a. B over a times, sorry, b over 2a and b over 2a. b over 2a plus b over 2a is b over a. And b over 2a times b over 2a is b over 2a squared. So to factor that, we get x plus b over 2a all squared. And then these two terms are still chilling. You still have your minus b over 2a squared and your plus c over a. And this might not look like the quadratic formula, but we're actually very, very close now. That was the hard step. Next, I'm going to take these terms over here, move them to the left-hand side, right? Remember, over here is a 0. And then I'm going to take square roots, and then we'll just kind of rearrange things until it looks like the quadratic formula. So let's do it. I'm going to add this to both sides and subtract this from both sides. So I'll have b over 2a all squared minus c over a is equal to x plus b over 2a all squared. Before I take square roots, let me clean up this left-hand side. B over 2a all squared is b over 2a times b over 2a. That's b squared over 4a squared. And then minus c over a is still chilling. And on my right-hand side, I still have parentheses x plus b over 2a all squared. If we have a common denominator, between these two terms. This guy's denominator is 4a squared. This guy's denominator is a. So if I multiply by 4a over 4a, then I can write that left-hand side as b squared minus 4ac all over 4a squared. And this is still equal to x plus b over 2a all squared. And we start to see those familiar pieces of the quadratic formula showing up, right? B squared minus 4ac, we know this. This is the piece under the square root. Oh, and my next step, if I'm going to solve for x, is to get rid of the square. So I'm going to take square roots on both sides. So big square root with a plus or minus out front, because we're taking square roots on both sides of an equation. We always get a plus or minus. Inside here is b squared minus 4ac all over 4a squared. Just taking the square root on the left-hand side. When you take the square root on the right-hand side, the square goes away and you just get x plus b over 2a. Now we're very, very close. I can give the square root to the top and the bottom separately. So I get plus and minus square root b squared minus 4ac. The square root of the bottom, 4a squared, is the square root of 4 is 2. The square root of a squared is a. Uh-oh, this is looking more and more like my quadratic formula. And this is equal to x plus b over 2a. Now I'm going to take things back up here. If I subtract this b over 2a from both sides, I'll have negative b over 2a plus and minus the square root of b squared minus 4ac all over 2a equals x. And that is your quadratic formula. These two pieces have the same denominator, so you can write them as one fraction. And I can put the x on the left-hand side, say x is equal to b plus or minus the square root b squared minus 4ac 2a. And that's what we wanted. That's the quadratic formula. We are done. So that's the proof. I like thinking of it this way, because this way you can see the geometry. You may remember that this piece right here, this is h, the x-coordinate of the vertex, which means that this piece right here is that distance we talked about earlier. So what the quadratic formula says is start at negative b over 2a, your vertex, your axis of symmetry, and either walk to the right this amount or walk to the left this amount. Either way, you will get to one of your x-intercepts. So this vertex down here is the point h comma k, which means this guy right here is h. Your x-intercepts are the x value here and the x value here. So if I call this distance d, we said earlier this distance is the same, right? Which means this x-intercept right here is h plus d. And this x-intercept right here is h minus d. Where d is that distance, the square root of b squared minus 4ac all over 2a. So this way of thinking about the quadratic formula is really nice. And it's actually how the thing was discovered. Most formulas for roots of polynomials, there is a cubic formula, a formula for the roots of a degree 3 polynomial. There is a quartic formula, formula for the roots of a degree 4 polynomial. All of those employ some symmetry arguments to make the algebra manageable, because otherwise it's quite hard. You know, coming up with all of this bare bones is tricky if you don't kind of know what you're shooting for. And I encourage you guys to think of the quadratic formula this way rather than this way. Obviously, they're equivalent. They say the same thing. And I know when you're plugging in to find answers, you'll probably do this. But just remember that it can be thought of like this, like start at the x-coordinate of the vertex and walk left or right some amount. It's going to be the same amount either way to get to your x-intercepts because you have this symmetry. And then that amount is the second piece from the quadratic formula. So the first piece tells you where the vertex's x-coordinate is, or what your axis of symmetry is. And the second piece tells you the distance you have to walk either to the right or to the left. Cool shit, right? So that's your proof and geometric interpretation of the quadratic formula. I trust that you guys have some practice with this, but just for fun, we can, let's grind out the roots of that thing we completed the square on earlier. All right, are we comfy with this? Any questions we would like to ask about this proof? Okay. So I know you've all done plenty of this. I just want to get you a little bit of practice, because if I didn't do it, that would be bad. Ooh, that's not going to work, is it? Yeah, no, I'm going to have to use something else because this doesn't have any real roots. Let's find something that does have real roots, just not nice ones. How about 2x squared minus 12x plus 13? So let's find the roots of this guy. We can try to factor.
Professor, the screen is really blurry.
Oh, I'm sorry. Document camera not doing its job. There we go. Oh, come on, focus. All right, so you can start by trying to factor. Here, a times c is 2 times 13 is 26, and b is negative 12. So we want two numbers which multiply to 26 and add to negative 12. Can we find two such numbers? Well, in general, the way you do this is you look at all the ways to write a times c as a product of two numbers. So 26 can be written as 2 times 13. But since both of those are prime, there's no other way to decompose this, right? There's no other way to write 26 as a product of two numbers besides like 1 and 26. And no matter how you do this, they're not going to add up to negative 12, right? You could take either of these to be negative or either of these to be negative. And there's no way to get to add -12. So we can't factor. We're stuck in the water here, right? That step that we need to begin the factoring with, where you find those two special numbers, whatever, can't do it here. There are no two integers that multiply to positive 26 and add to -12. So what do we do instead? We use the quadratic formula. And that says that this function will be equal to 0 if and only if x is equal to, sing it with me now, -b, that's -12, is positive 12, plus or minus the square root of b squared, -12 all squared, minus 4ac, 4 times 2 times 13, all over 2a, which is 2 times 2. And we can try to clean this up. We should. We absolutely should. That's 12 plus or minus the square root of 12 squared is 144 minus 2 times 13 is 26. 26 times 4, well, 25 times 4 is 100. So 26 times 4 is 104. Downstairs, 2 times 2 is 4. What is this? That's 12 plus or minus the square root of 144 minus 104 is 40. And the square root of 40 well, that's the square root of 4 times 10. Right? 40 is 4 times 10. And square roots play nice with multiplication. You can take the square root of the 4 and the square root of the 10 separately and just multiply them. The square root of 4 is 2. So this is 12 plus or minus 2 times the square root of 10 all over 4. So your two solutions are 12 plus 2 times the square root of 10 all over 4. The other one is 12 minus 2 times the square root of 10 all over 4. And we can clean these up. You can split this fraction up across its numerator, that's 12 over 4 plus 2 root 10 over 4. Over 4 is 3, and 2 root 10 over 4 is root 10 over 2. And the same sort of thing can be done with the other guy. That's 12 over 4 minus 2 root 10 over 4, versus 3 minus root 10 over 2. So these are your two answers. And they're not nice numbers, they're irrational, but they are real, at least, which is nice. I want to talk to you about what happens if these guys are not real numbers, or how that can arise. Any questions on what we did here? How we knew not to continue trying to factor, or how we used the quadratic formula, how we simplified the square roots, how we simplified the fractions, any of that stuff. All good? Okay. Somebody in chat earlier mentioned the discriminant. The discriminant is a portion of the quadratic formula. It's the b squared minus 4ac part. It's the part that goes under the square root. If b squared minus 4ac is positive, then the quadratic has two real roots, two x-intercepts. Because your formula will have, something plus or minus the square root of that number, which, exists all over 2a. So you're going to have two answers. You'll have one from the plus and the one from the minus. If the discriminant b squared minus 4ac is equal to 0, then the quadratic has one real root. Right? Because the piece under the square root is 0, the plus and minus doesn't matter anymore. You just have, like, here you'd have 12 over 4, you'd have 3, which is just one number. So if the square root piece doesn't give you anything, then the plus and minus really doesn't matter. You just get one answer. And then the gnarlier case, if b squared minus 4ac is negative, then when you plug into your quadratic function, or sorry, you plug into your quadratic formula, you're going to be taking the square root of a negative number. So the quadratic has no real roots. Right? The square root of a negative number is not a real number. Now, what is true, and you may know this from previous classes, if you take the square root of a negative number, you get non-real complex numbers. So what's true here is that instead you'd have two non-real complex roots. Now for now, we're not going to worry about those, but I will talk about complex roots down the road when we talk about complex numbers in a later section. Okay. Any questions about the discriminant? This can be a useful tool. If you're starting to look at a quadratic and you're going, should I try to factor this? What should I try to do? If the discriminant is negative, you know not to bother factoring because there are no real roots, so the thing can't possibly factor. If the discriminant is positive, but not a perfect square, then you know that you're going to have a weird square root in your quadratic formula, something like we got here, which again means that these x-intercepts, these roots, are not nice numbers. They're not integers. They're not even rational numbers. So again, you wouldn't bother factoring. So what I do, if I'm confronted with a quadratic and I'm kind of stumped trying to factor it, but I don't want to just dive right into the quadratic formula, I just compute this little piece. And if this piece is not a perfect square or is not positive, I know to stop trying to factor, just jump into the quadratic formula. And conveniently, the most complicated piece of the quadratic formula I'll have already computed. So it's a nice tool. Okay. What else would we like to do? Not much else for quadratics, really. Mins and maxes are what you would think, right? If there's a min, a quadratic always has a min or a max. It's always at the vertex. If A is positive, that means the graph looks something like this. So you have a min at the vertex. And if A is negative, then your parabola opens down. That means you're going to have a local max at the vertex. Now these mins and maxes here, they're not just local, they're also what are called global or absolute mins or maxes. But we haven't addressed the difference between local and global extreme. That's actually not a part of this course. So we don't need to stress about that too much. But you know, if you're looking for the min or the max of a quadratic, you're looking for the vertex, right? Which means you want to complete the square, put the thing into that vertex form, then you can read it off. And that's not bad. So let me do a quick example here, and this will end our discussion on quadratics. Nice and clean. So let's find mins or maxes, graph, and give intervals of increase and decrease for the quadratic f of x equals negative x squared plus x plus 2. So all of these things revolve around having the graph and knowing the vertex. So what I want to do is complete the square. I want the vertex. So we're going to complete the square. So I start by factoring out that lead coefficient, which is just a negative. And this will give me negative parentheses x squared minus x minus 2. Then I take my b over 2a. I add and subtract that magic number. So here, a is -1, b is +1, and c is 2, right? So my magic number is b over 2a all squared. What is that? That's 1 divided by 2 times -1 all squared, which is -1/2 squared, which is +1/4. Right? -1/2 times -1/2 is +1/4. So I'm going to take that magic number and I add it and subtract it right after the x term. I leave everything else alone. And then we look at just those first 3 terms. X squared minus x plus 1/4. Cool trick. The b over 2a piece here is kind of always going to be what you use when you factor this. So even if you don't see how to factor x squared minus x plus 1/4, you know it's going to be x minus 1/2 all squared, because the inside of your magic number was a -1/2. And then you still have minus 1/4 minus 2. I can distribute the negative. I get negative x minus 1/2 squared. And then minus 1/4 becomes plus 1/4, minus 2 becomes plus 2. And if I have a common denominator between these two pieces, 2 can be written as 8/4. So this is 9/4. So this is negative, parentheses, x minus 1/2 squared plus 9/4. So that is my completing the square done. Any questions on the completing square here? Okay, so my lead coefficient is -1, h is positive 1/2, and k is 9/4. So my parabola has vertex one half, comma, 9/4. 1/2 is 1/2, 9/4 is like 2 1/4. So let me mark this as like, mark this as 1, 2, 1, 2. So 1/2, comma, 9/4. It's going to be like right here. And my parabola is going to look something like this. These x-intercepts we can find if we want to by using the quadratic formula. These guys here. But we're just looking for mins, maxes, the graph, and intervals of increase and decrease. So I don't actually care what the x-intercepts are for this problem. This point is obviously a max. The location is x equals 1/2, and the max value is 9/4. Who can tell me where this function is increasing? Where this function is decreasing. Somebody help me out a little bit. Where is this function increasing?
-infinity to 1/2.
Very good. Yeah. This whole part of the graph is increasing, and we always give this as an interval of x values. So from -infinity up to this x value, which is 1/2. And we're decreasing then from 1/2 to positive infinity. Questions about this? All right, well then that is our quick and dirty run through of everything you need to know about quadratics. In the last few seconds here, I think, what time is it? I have you guys for this. Oh no, we're a little bit over time. Let me just introduce the terminology for the next section here, and then I'll let you guys go. The next section is on polynomials. And I just want to define these things for you. A polynomial of degree n is an expression of the form p of x equals. So by degree n, what we mean is that x to the n is like the largest power of x that shows up. And n here should be a non-negative integer. A whole number, which is not negative. There's allowed to have a number attached to this, right? Like 3x cubed or 5x to the 4. The number attached to x to the n, we just call it an. And then you're allowed to have lower order terms. So the next term would be like x to the n minus 1. And he has a number attached. We call that a sub n minus 1. And it continues down like this, going down, the power going down by 1 each time until you get to x to the 1, whose attached number we call a1. And then the last term, which doesn't have an x attached to it at all, we just call that a0. So an, the constant attached to the largest power of x, we call this the coefficient. A0, we call this the constant term. And the name for the numbers an minus 1, and so on, is coefficients. We require that an is not 0 for the same reason we require that a in ax squared plus bx plus c is not 0, because otherwise this term wouldn't really be here. And the other, all these terms, an minus 1, these are all just numbers, an minus 2, all the way down to a1 and a0. These are called coefficients. So an is called the lead coefficient because it's the coefficient on the highest order term. But in general, all those numbers are just called coefficients. Alrighty, I'm going to go ahead and let you guys go here. We are going to pick up on Thursday talking about polynomials and their graphs. We're going to learn a lot about how to factor polynomials. We're going to learn how the factors affect the shape of the graph. We're going to learn about something called end behavior, which is like which way do the arrows point on the graph, all that good stuff. We will learn on Thursday. Then we're going to learn how to divide polynomials. We're going to learn something called the rational roots theorem, which is a big tool for helping us factor polynomials that are kind of large and scary. We're going to talk about complex numbers, all sorts of stuff. So next time we are going to discover a lot more things about polynomials, and we'll be talking about polynomials and ratios of polynomials for the next few classes. So please dig in. I'm going to open a new homework for you guys in the next few minutes. It's just going to be this very basic quadratic stuff and the definition of a polynomial. I don't think you'll have a hard time with it, but please work on it between now and Thursday. That way on Thursday, you'll be up to speed and ready to charge forwards. That's all I have for you guys today. So unless there are any burning questions for me, I'll go ahead and end the meeting here. Is there anything you guys need from me right now? Okay, I'll go ahead and end the meeting then, and I'll see you guys on Thursday.